So this video is on collision theory and chemical kinetics. So it's all about how do we increase rates of reaction. And so rates of chemical reactions has to do with how fast do these reactions occur? What can we do to make a reaction go faster? What can we do to make it slower? In fact, depending on what you do with your life, for example, as a chemical engineer, I took a whole semester class on chemical kinetics. A lot of times people run into chemical kinetics in the form of enzyme kinetics, and that's more a biology connection. So you might be surprised where you run into this. So the amount of time it takes for a chemical reaction to come to completion is called the reaction rate. And so reaction rates will differ depending on different reactions, and the rates of reaction are related to the properties of particles through a model called collision theory. So what is collision theory? Well, particles will only react if there's an effective or successful collision between them. So I like to think about walking through the halls. So if I'm walking through the halls and someone kind of nudges me, I'll just keep on walking. Okay, so they didn't really have very much energy. They didn't necessarily hit me right in the face or anything. So yeah, that's not a big deal. However, if I'm walking down the hall and someone decides to punch me straight on in the face, I think we might have a bit of a reaction. In fact, I think that would have enough energy to get that reaction started. And if they got me square on in the face, then I probably would react because I had proper orientation. So the key to collision theory is that first off, those molecules have to collide, and second is that correct orientation. By doing so, we're going to form that activated complex. And if you'll notice here, the activated complex is that peak part of that energy diagram we saw with thermochem. So it's really a transition state between your reactants to your products. And so what happens is your reactants are breaking up and they're going to form these products, but there might be some kind of things that get formed in between before it gets to that part. Now, the amount of energy needed to make that reaction occur is called the activation energy. If you recall, it's the difference of that energy hill, and we used the abbreviation E sub A. So here's a visual for that. And so we can see an effective collision is this first one here. So you'll see we have chlorine with this molecule NCLO. We have this effective collision. It goes right in the perfect orientation with enough energy. And so you can see after collision, we now have two different products as a result. If we look at this ineffective collision, you can see they're headed towards each other. They react, but it's not kind of perfect. And so they're just kind of bouncing off each other. And notice we have not the two different products, but we ended up with the same two reactants. So that means the collision didn't quite work. There wasn't either enough energy or the orientation wasn't quite right. So I like to think of things in terms of increasing the rate of reaction. So the rate of reaction can be increased by changing certain factors in a reaction. And so these are the main factors I do want you to know. One is increasing the temperature. So if we increase the temperature, molecules will move around faster. If they move around faster, that means they're going to hit each other more and then cause a reaction. If we increase the concentration of reactants, the same thing. You'll have them move around more, and by moving around more, they're going to hit each other and also cause a reaction. If we increase our surface area, the same thing would happen. So I like to compare powdered sugar with a sugar cube. Powdered sugar is going to react really quickly, whereas a sugar cube is going to take some time. We can also stir things or agitate things. That could also make things move around faster, causing them to react. We can increase pressure as well. This would only work for gases. So you can think of the piston example that I've shown you before. You have a piston, right? And if we push this piston down, you're going to force those molecules to have less space, and that forces them to react. And that weaker bonds will react faster than stronger. So if those bonds are easily broken, they're going to be more willing to react. So all of these factors will increase your reaction rate because they produce a greater number of effective collisions. And a greater number of effective collisions can be achieved by any of those factors above. So we also have catalysts and inhibitors. So catalysts will lower that energy hill. So here you can see without an enzyme and with an enzyme. Here's a bio example. So catalysts will lower that activation energy, making it easier for the reaction to occur. Okay, and so it just lowers that activation energy. So you can see without an enzyme and with an enzyme. Catalysts are recycled, so they're going to be there at the beginning and the end. And if you have a chemical reaction go from A to B, if you see something on top of the arrow, like a symbol, a chemical symbol, that is the catalyst used for the reaction. In the biology world, enzymes are a catalyst. Okay, inhibitors will do the opposite and slow down the rate of reaction by increasing that activation energy hill. There you go.